Welcome everybody. So in this video we are going to look at how I do Churchill friction factors, okay, the fanning friction factor and all that. So the class first starts, I have a class called Churchill Friction Factor. I think the correct spelling is supposed to be 1H, but I'll probably have to change something later on. So I literally typed Church and Hill, but it's supposed to be Churchill, but probably deal with that later. Okay, so Churchill Friction Factor is a class that helps us return the Moody, Fanning, and Darcy friction factor. Moody and Darcy are pretty much the same thing, and I also recognize that there's more than one way of getting friction factor. You do not have to use the Churchill correlation. That's why I made this friction factor interface right here. So in case that someone else wants to in case maybe in future I want to use a different way of finding friction factor, I can. Okay, so this is the interface you'll find, and you'll find it over here, the I friction factor interface. And what the interface does is to provide three methods here, three method declarations. One is called fanning, then you have Moody and Darcy. Moody and Darcy are physically speaking the same thing, but in case you are comfortable with one or the other, you can just use it. All right, so that's the idea. Okay, but the way the Churchill friction factor class works as of June 2022, 16 June 2022, there are a few terms that you need. Okay, so I think it's good to use Visual Studio because I really cannot see formulas here. So let's see this. I'm going to close documentation, close test. Let me open this up to math, friction factor, readme.markdown. Okay, so this is the friction factor, and then yes, we will be able to see. So I want to open up the pipes and valves readme. I'll open it to the side, and I want to look for Churchill. So let me look for Churchill. Churchill friction factor. Okay, maybe it's inside the. I suspect it's inside the what do you call that? I suspect it's inside the fluid pipe theory documentation. Yeah, I think this is better. Yes. Okay, so fluid pipe theory documentation. So let's just copy and paste the Churchill formula. Let's go up. Where's the Churchill formula? Yeah, here's the Churchill formula. Yeah, let me copy the A and B terms first. Yeah, it should be right here. So let me copy the A and B terms first, yank it, and then I will basically paste it over here under the friction factor readme. Okay, is defined by, okay. So remember we have a A and B kind of a thing going on here. So and then what else do we have? Friction factor readme. Let's go back to the fluid pipe theory. Then I'll just copy and paste the friction factor formula. Okay. 3 down, yank, and I will paste it here. Paste it here. Okay, so this is the Churchill friction factor, and just be mindful that this is a fanning. Okay, if it's a Darcy, okay, XX, let me delete that. So CI, curly brace, okay. The Darcy friction factor will be, let me put here number 8. Yeah, so this is how the Churchill friction factor is calculated. Fanning friction factor is 2 times this, all of these things in here, 8 over RE to the 12. This is the laminar term, and you have the turbulent term to the right. A and B are defined by the following, and that's it. Okay, so there are a few parameters you need to supply: the Reynolds number and the roughness ratio. Okay, so my first order of business, okay, defining A and B. So there are two methods over here to help you define A and B. So let me copy and paste again. 3 down, paste. Okay, XX $. Okay, so well, this is A. A is here. A is defined in code as the following. So let's go to the code. Okay, now I'll go to Vim and I'll reload the file here. So where do you find A? Okay, so A is over here as a private method. A is defined as the following. Let's do 5 open escape. Open up there, and let's paste it here. And let's use the C# code block. C#. Yeah, yikes. C# code block, 14 down. Yep. Then go up, 11, indent. Okay, there you go. So, how do I do it? Okay. So there's a Reynolds term and the roughness term. Okay, this Reynolds term is 7 over RE to the power 0.9. So this is this 7 over RE term here. The roughness term is 0.27 times the roughness ratio. Should be quite straightforward. Okay, then the log fraction is actually equals to 1 divided by all of these things here. The Reynolds term, which is this thing at the bottom, plus the roughness term, which is also at the bottom here. Okay, so yeah, let's just see whether the Churchill correlation is correct. You want to make sure it's correct. So there's no power or anything at the bottom. It's just these two terms. Okay. And of course, if you take a look here, the factor of A is being used because this is Darcy friction factor. So I make this distinction right here for you. Okay, the log fraction is here. So the thing that you actually take a logarithm of is called the log fraction. Okay, the inner bracket term. What is this inner bracket term? Inner bracket term is whatever is inside these square brackets right here. Okay, see everything inside the square brackets. And then A is math, okay, power. I use the math power function again. Whatever is the inner bracket term, I put it to the power of 16, then I return. So this is the method for A. Okay, nothing too complicated. Then I'll go down, fall down, yank this, and I'll put this at B. Okay, 5 open, exit, and insert C# code. Here, 1, 2, 3, backticks. Now paste it here. So, okay, B is also pretty straightforward. The numerator is just this 37530 to the power 16. Denominator is Reynolds number to the power 16. Then I return the numerator divided by the denominator. Okay, that's it. Okay, so I save both of them. Let me close or open it again. So yeah, close and open so that I can have an A and B method. Once I have an A and B method, then the rest is also quite straightforward. Okay, so let's take a look here. What I do. Okay, I actually start to define this thing called the Churchill inner term. Alright, Churchill inner term. Alright, let's go down. Okay. Churchill inner term. Okay, I'll just call this intermediate calculation. So I'll put a C# here. C sharp, another C sharp. Oh, 7, 8 down. Okay. C sharp term here. Alright. So, what I have here, we close, open up again. What I have here is this intermediate calculation where I have a laminar term. Okay, so the Churchill inner term is whatever is inside this 1/12 bracket. Okay, so let me just copy and paste that for you. Okay, 3 down. Let me put it here. Okay, official X. Okay, I'll just call this the inner term. Okay, so this is the inner term there. You have a laminar term on the left hand side because this is actually the laminar term. 8 over Reynolds number to the power 12. Turbulent term is this thing on the right. Okay. So turbulent term is 1 over A plus B. So I make a double called A term and I call the A method. Okay, and I feed in the Reynolds number and roughness ratio. I get the B, which is over here, B, which will get this B term here, and then I'll have the turbulent term. Okay, it will be math dot power 1 over A term plus B term, so you can see that it's very straightforward. Okay, then you have 3.0 over 2, not 3 over 2, 3.0 over 2. Why? Because you need to tell C# that you're starting out with a double rather than an integer. If not, it will think that the number 3 is an integer and it will perform integer math. Then you will not get the 1.5. Okay, so we have this inner term. Okay, and then after that, we just return our fanning friction factor. Okay, that's okay. 5 down, yank, and here will be fanning friction factor. Now I will C#, paste the code here, go down, indent, save. Okay, so to calculate fanning friction factor, okay, what happens is that we just have the number 2. We just have the number 2 times, okay, we'll just do a math power law, and then you just power it to 1 over 12, right? 1 over 12. So I just multiply this inner term by I'll make this inner term by I will have this inner term over here. Now power it to 1 over 12 and then I times 2. That's all. So I mean, other than that, it's nothing too much to it. Okay. So quite straightforward, yeah. 3 down, yank, go all the way to the end. Okay. So I think that's it. Usage, okay, just instantiate the object and use the fanning friction factor term straight away. Okay. Darcy and Moody friction factor methods. Okay, so the Darcy and Moody friction factor methods are as follows. Okay, what do I do with the Darcy friction factor? Okay, for Darcy friction factor, I'll just multiply 4 times the fanning friction factor. Okay, 4 times the fanning friction factor. So that's all this thing is doing. Okay, Darcy friction factor just multiplies fanning friction factor by 4, and then okay, let me load the file, and then I'll have a C# here, and I'll go 9 down, backtick 3 times, 7 up to the left. Okay, done. So multiplies the fanning friction by factor by 4, you can see, and yeah, the Moody friction factor is just Darcy friction factor. It's the same. Okay. Moody friction factor just calls the Darcy friction factor method. Okay, I didn't even copy and paste the same code. Okay, I didn't even copy and paste the same code so that now I can save myself some okay, it's not updating fast enough. Hello. Update. Alright, whatever. I'm just going to let me reload the buffer. So I'll just do B#. Okay. Maybe our B#, BD#. Q. I'll quit this. V split. Okay. Where am I? Up the directory. Up the directory. Go to math. Friction factor. Readme.md. Okay. Now BD this as well. Let me open this again. Yeah. Yes. Now I have my C# code block. It doesn't work flawlessly, but it will still work. Okay, so you can see that this thing actually just loads up here, and okay, just for this, how to use it, just instantiate the object Churchill Friction Factor. Just make the Churchill Friction Factor object. Use the method straight away. There's no constructor, nothing at all. Okay, that's all for friction factor. Yeah, so next thing here is, let me check. There are lots of papers flying around. Okay, next thing is the derivatives. Okay, next thing is to do derivatives, because we'll need to do Newton-Raphson method, so we need a way of finding derivatives. So okay, what happened? I'm gonna mess up the files by accident. Oh public. Okay, I messed up the files by accident. Okay, there we go. Alright, what is next? Next thing in line will be derivatives. So let's open the derivatives up. I'm going to copy this readme, and I'll put it in the derivatives. Okay, readme.md. Yeah, I'll try to make it short as possible. So let's open the readme.md, and I'll do a V split here. Maybe I'll close this tab. Tab close. Actually no, this one is okay. And this is for my Git Ranger. Okay. Open this up here. FrictionFactor.readme. And on the right, I want to open up the I derivatives. Okay, that will have to do. Okay, so this is the math derivatives meet. Okay, what is this here to do? So I'll Shift G and cancel everything as usual. Okay, the derivative class is here to perform numerical differentiation. Okay, so okay, let's see. I derivative. Since there are many ways of performing numerical differentiation, okay, I gave an I derivative interface. Okay, and this is all it is using system. And I'll put a C# here. C# code, paste it, and that's done. Okay, whatever goes on under the hood can fulfill this interface. Okay, so derivative classes can use this I derivative interface. Okay, so there are multiple ways of doing it. One of them is, of course, using existing code. That is the most efficient. Mathnet Numerics. Yeah. However, over here you will not see any, at least in the documentation, I could not find easily anything about derivatives, though I did see something about integration right here, like Simpson's rule, Newton Cotes trapezium, all of that. And so, how did I know there's derivatives here? Let's go to Mathnet Numerics. Okay, open in a new tab, GT. Okay, then I will go to the source repository. Yeah, so this is where the source repository is. Okay, I had to actually go into the source, and then I will go to numerics, and then you see this thing here, differentiation. Okay. So you see that there's a numerical derivative.cs, Hessian, Jacobian, finite difference coefficients.cs. Okay. However, to use this, I think this is the way we can do. This is the way we can do. Okay. There's a namespace Mathnet Numerics. Okay. The class to use is this public static class differentiate. Okay. We can actually perform a derivative. We load in this. I think I better drink water. Yeah. Anyway, so there is a public static double derivative. These are static functions, meaning to say you don't even need to instantiate the class, and you're not supposed to instantiate the class because it's a static class. Okay. You don't need to instantiate the differentiate class in order to use the derivative function. Okay, inside the derivative function, we have derivative. It will be func double f. So a function double is okay. Let me bring up the documentation. Let me do. Whoops. Okay, function C#. Okay. Local functions GT. So this is it. Oh, wrong one. Go back. Oh, there is no back. Yes. Funcs C# delegate. Okay, this is a delegate. Yeah, this I think is the correct article. So the C# function here, okay, this thing actually encapsulates a method. There's one parameter. Okay, so this is the in parameter, and it returns a value by the type specified in a T result parameter. So this is the T result parameter, and it has an out keyword. So this is the input, this is the output. Okay, so there are some arguments that are in here of the type T, and this T result here will be the T result outside. So this is a delegate. So meaning to say, any function, any method that fits this pattern, let's say I want a double in and a double out, okay, especially for this case, the derivative function, you have a double in and a double out, you can actually just stuff it in there. You'll have a double x also that you need to put in, and this will actually tell you what is the value of x for which you want to, where do you want to perform your numerical differentiation. Order is it the first order or second order derivative? That is it. In fact, easier still for you is to use this first derivative function. You don't even need to specify the order here. Okay, there's also a first derivative function, but this one will be easier to use, so don't need to bother with that. Okay, there's a second derivative as well if you want. And quite interesting here, we have a partial derivative. Okay, so what's the partial derivative here? Partial derivative here, it takes in an array or list of doubles. Okay, so this is a double array. Okay, this is a double array, so it takes in a double array. It actually also puts out a double array. Okay, int parameter index int order. Okay, so so this order thing is the same. You can just use the first partial derivative here. So this f is the function which I was talking about. X is the vector with which to evaluate the derivative, meaning to say that if let's say you have a roughness ratio and a Reynolds number, and the roughness ratio is constant, I mean you can still put in the Reynolds number and roughness ratio, but you tell this derivative function which is the one which you want to do this partial derivative. So you need to specify that using this thing called parameter index. So it says index of independent variable for partial derivative. So we'll probably be using this one a lot later on. However, I don't have the I don't exactly have the type here. So yeah, this is something like work in progress. In fact, when I first started, I didn't even know that I can just use this numerical differentiation library right here. Of course, you can take a look at the source code, but I actually make my own source code, make my own thing right here. It's called central difference, because this is a central difference approximation. Okay, so this is the central difference. It's an in-house code. Okay, so what do I have here? It's a fair bit of code. Yeah, it's a little bit much, in fact. Okay, so let's see. There's a lot of checks here. Okay, but let's go all the way to the bottom. And yeah, this is a bit overkill. Yeah, but why am I putting all this? Okay, the underlying code that actually happens is actually this. Pardon me, need to clear throat. I should have done it away from the mic. Okay. So the central difference approximation, the base at the end of everything. Okay. No, excuse me. So I have a y plus and a y minus. So this is the function evaluated at slightly more than the step size. This is the function evaluated at slightly less than the step size. and the approximate dy dx equals to, well, y plus minus y minus divided by the step size. So the step size is divided by 2 over here, and that's how I code it in. Then I return this. Okay, so that's basically kind of all you need. Okay, but I did not want to have a step size at all. I don't want the end user to define the step size, because that's way too much extra work to do. So I didn't want the user to think of step size, so I have an in-house step size. Okay, so what this thing basically does is that I'll define a step size. Okay, I defined an initial step size. Okay, so I define an initial step size, and then the next iteration of the step size is the step size divided by 2. Okay, and then I will keep repeating, I will keep calculating like methods. Okay, so I have a dy dx and a dy dx new. So I did a central difference approximation for both of these, the same method. However, I used the step size for this one and the new step size for this one. Okay, next thing I did is to calculate a relative error between both of them. Okay, and once this error is less than some tolerance, okay, once this error is less than some tolerance, I will just return the value. Okay, so I designed the loop to differentiate and reduce step size until some convergence is reached. So this is basically the limit theorem. Okay, C#. So oops. Okay, so yeah, basically I keep doing it until I find the what do you call that, the correct derivative. So let me go 32 up, yank. Okay, I have a while loop to do this for me. Okay, okay, so the code, while there's a lot of things here, is pretty simple in concept at least. Okay, so while the error is more than the tolerance, you keep repeating this step size reduction until you reach the correct number. So yeah, if I get the error less than some tolerance, then dy dx and dy dx new are about the same. Okay, then I will just return dy dx. Okay, why do I have this check number validity? Because sometimes if you have graphs like 1 over x, where the derivative actually goes to infinity near 0 and is undefined at 0, sometimes this code can actually return not a number. Then you kind of need to check that. Okay, so I have this check number validity code to help with that. Okay, otherwise it's pretty much normal, correct. You can keep doing it. Okay, so if it doesn't pass, then I will say derivative is badly behaved. And derivative is badly behaved. I basically copy and pasted some of this code, and I made it inherit by a divide by 0 exception, because that's the definition of what this is very related to what badly behaved derivatives are about. So that's the idea. Okay, that's the idea. So that's why I have all this try and then check number validity, so that I can find out, you know, if there's some derivative that's badly behaved, goes to infinity. Okay, if there's some number that's badly behaved or goes to infinity, I will throw an error. Okay, so if I have a lot of checks to see if the number goes to infinity, right, is if the derivative goes to infinity. So that's what I'm doing here. C#, paste, to indents, fall down, open. So yeah, you can go read that in your time. So the idea of all these checks are so that, you know, if it happens to be a very infinite value, I will throw you an exception and say, yeah, something is wrong. Please go and make sure it's there is a valid derivative that you can calculate. So this is the basics of this derivative function. Okay, so yeah, I think that's enough. I have already a central difference thing. Yeah, and then of course there are some tests I did, but I think that's enough. This is how I did my derivatives, and I'll probably go and write more code, and then I'll just document it in front of you as I've been doing over here. Okay, thanks for watching.